In this talk, I will introduce our work, Personalized Dual-Level Color Grading for 360-degree images in virtual reality. I'm Lin-Ping Yuan from the Hong Kong University of Science and Technology. This work is a collaboration with the University of Cambridge. Color grading is a crucial editing process where creators adjust color parameters, such as contrast and white balance, to achieve a desired look or mood, reflecting their personal tastes and preferences. Since color is an important way to guide user attention in a 360-degree environment, color grading usually involves global color adjustment for an entire image and local color adjustment of a point of interest. Since the perception of local colors is influenced by their contextual colors, local color adjustment needs to consider the established global colors. Manual color grading is difficult since creators need to experiment in a high-dimensional search space to find parameters that match their preferences. A popular approach to alleviate the difficulty is modeling color personalization as a black box optimization problem, in which we need to find the best set of color parameters that maximize a latent user preference function. This figure shows a framework for solving the black box optimization problem, where we need to repeatedly query the function values at various locations to find the global optimum. Bayesian optimization follows this framework. A variation is preferential Bayesian optimization, which uses relative assessment by comparing two options as feedback, rather than using absolute scoring for a single option as feedback. It is easier for people to do comparison feedback rather than absolute scoring. By using preferential Bayesian optimization, many algorithms have been proposed for personalized color design. Although they are effective, they only focus on optimizing a single and constant latent objective function. Moreover, their desktop-based user interfaces are intended for general 2D images rather than for comparing 360-degree images in VR. To address the limitations, our method aims to enable dual-level color personalization for 360-degree images, consider the influence of global colors on local colors, and support effective color comparison for 360-degree images in VR. To achieve these goals, we formulate the dual-level color personalization as a dual-level black box optimization problem. The objective is to maximize the aggregate preference across the entire image and the local area. And the local preference is conditioned on the selected global color parameters. In response, we propose a dual-level PBO framework to solve the dual-level optimization problem, which consists of 3 stages, including modeling user preferences with Gaussian process, identifying informative query points, and engaging users for comparison feedback. In stage 1, we propose a novel context-aware preferential Gaussian process for contextual preference learning for local colors, which considers the influence of global colors. In stage 3, we design and assess 3 VR interfaces that allow creators to compare colors. To model user preference in stage 1, we explore a standard preferential Gaussian process for global preferences. For local preference, we propose a novel contextual-aware preferential Gaussian process. It combines a multi-task Gaussian process for handling global colors as contexts and a standard preferential Gaussian process. There are some technical challenges for learning local preferences. This figure illustrates 2 iterations of our algorithm. Unlike the global preference function is static, the local preference function keeps changing since it is conditioned on the selected global parameters. The observed local function values are all queried on the previous contexts, making the query points sparse, and the current selected global point an unseen context. To address these challenges, we cluster the seen global contexts when calculating the kernel and use regression to guess the local function values under the current global point. We conduct experiments to assess the effects of clustering seen contexts into different numbers of groups and investigate the effectiveness of different regressors. The results show that reducing the number of contexts does not compromise training accuracy. However, selecting a proper number of discrete contexts for a given parameter number can significantly output continuous contexts in prediction, regardless of the regressor used. Here, we show the color grading process and results of a standard PBO adjusting global colors and our dual-level PBO adjusting global and local colors. This illustrates that our dual-level PBO offers greater creativity flexibility to achieve detailed effects, such as varying local hues from global hues or fine-tuning brightness levels. In stage 3, we consider 3 VR interfaces as a part of our dual-level PBO framework to compare color-graded options and judge the preferred option. The side-by-side interface adapts typical desktop interfaces to display equal rectangular projections side by side. The sequential interface wraps users within one 360-degree options at a time. The partial user interface divides the entire VR space into equal areas, with each area displaying the same slice of 2 options. To figure out how well each user interface supports color comparison in VR, we conducted a controlled user study with 18 participants. We considered 6 conditions. This figure shows 3 conditions. The other 3 conditions are the 3 types of interface, but with 4 options. We asked participants to rate the conditions from different aspects. We log their completion time and head movement angles. We also asked them to rank the 3 displaying modes on the different settings. Here, we show some examples of how the participants' facing direction changed over time. For side-by-side, users' head movement was small and within their field of view. For partial, users moved their head centering on the dividing line. For sequential mode, user either made full turns for each option or limited head movement to a small section gradually. In summary, the sequential mode with 2 options is the most preferred, and the partial with 4 options is the least preferred. However, each displaying mode has its strengths and weakness, which we can combine in the VR color grading system. To conclude, this work contributes a dual-level PBO framework for dual-level color grading for 360-degree images in VR, a novel context-aware preferential Gaussian process, and an empirical evaluation of VR interfaces for color comparison. For more details, please refer to our paper. Thank you for watching this video.